Welcome everyone. In this video, we provide you with the basics of conducted emissions of electronic systems. We talk about the definition of conducted emissions, where they occur, and potential problems these emissions could cause. Furthermore, we discuss different modes of propagation and explain why this distinction is important for us as EMC engineers. We conclude this video by providing a short summary. Without further ado, let us dive straight into the basics. As the name suggests, the term conducted emission relates to unwanted transient signals that propagate via conductive materials. These emissions are caused by electronic-based systems, such as the block labeled as DUT, which stands for Device Under Test, and are propagated through the interfaces into the connected networks or systems. One of the most critical paths that these conducted emissions can take is into the power distribution network. Such a power distribution network usually connects a multitude of electronic systems via long cables. This allows the conducted emissions to propagate into other devices in two different ways. First, they can directly couple into other electrically connected systems via the power lines. The impact these emissions have on the other devices depends on their individual robustness against variations on the power lines. Second, the long cable connections of the power distribution network form large and efficient antennas for the conducted emissions. Therefore, the emissions are radiated of the cable connections and received by electronic devices in proximity, which can interfere with their normal operation. Due to the long cables of such power distribution networks, the formed antennas cause additional electromagnetic radiation at lower frequencies. To understand how such conducted emissions are propagated towards the power distribution network, we have to take a look at the different ways a current can flow through a system of N conductors. From transmission line theory, we know that in a system of N conductors, there are N-1 modes of propagation. These modes can further be subdivided into so-called common mode and differential mode signals. Differential mode signals arise from the normal operation of a circuit. The current flows in loops from the power supply to the system and back again. A pure differential mode signal has the same absolute value in both lines, but with different signs. Contrary, common mode signals have the same phase and direction in both lines towards the electronic system. The loop is then closed via coupling into a common ground line or plane where the current returns to the power supply. Typically, this common mode current is the main source of radiated emissions. With increasing number of power lines, the number of differential modes increases, while there is only a single common mode. For our N-conductor system, this means that we have a single common mode and N-2 differential modes present. The distinction between these different modes of propagation is important when it comes to choosing the appropriate countermeasure against conducted emissions. For most applications, filters are used as a countermeasure, and to design them, we must know the mode of propagation. With that said, let us recap on what we learned so far. Conducted emissions are propagated from a DUT into the power distribution network. From there, it can either be directly coupled into other devices or radiated off the cables and received by electronic devices in proximity. There are two different modes of propagation, differential and common mode. For the common mode, currents flow into the same direction and close the loop via a parasitic element and the ground wire or plane. Differential mode currents flow into the DUT on one line and back on the other. For larger systems with increasing number of conductors, the amount of differential modes increases, while there only is a single common mode. This common mode, however, typically is the predominant cause of radiated emissions. This video provided an introduction to our video series about conducted emissions. In the second part, we talk about different measurement setups and regulatory constraints, while in the third part, we give a detailed look on different filtering and protection measures against conducted emissions.